Yeah, welcome everybody. Welcome to this evening's TSU Mini Moon Seminar Series. It's a little bit late, 9 o'clock in the evening, but early morning in Maryland. And we are very happy to have to be able to invite Professor Christine Hartzell to give a talk on the electrostatic charging of the dust particles. But the talk will be very interesting because she's looking at it from a modeling and from experimental side, right? And even from observations. So it's a very unique presentation. And we know that Christine, she did her undergraduate at Georgia Tech, and then went to Boulder, Colorado, did your PhD under Professor Daniel's chairs, right? Yeah.
Yep, that's right.
And then she's now in Maryland, building up a very interesting and strong group called Planetary Surface and Spacecraft.
Yep.
Laboratory. How she could put these two things together is a wonder.
It was a difficult name to come up with.
Right. But it's a very interesting, very nice name. Okay, Christine, please.
All right, so I'm going to talk today about electrostatic dust motion on small airless bodies. I'm going to talk a lot about asteroids, but this is all also relevant to the moon. I have two main co-authors on the talk today, Mike Zimmerman at Johns Hopkins APL. He did a lot of the plasma simulations that I'm going to show. And then my grad student, Charles Pett, he did the experimental work that I'm going to show at the end of the talk. Okay, so just an overview about my research interests generally. I'm interested in granular materials that are dominated by non-gravitational forces. So granular materials, typically we think of these as like regolith or dust on the surface of an airless body. And then non-gravitational forces are things like cohesion, electrostatics, magnetic effects. And I'm interested in applications to planetary science. So how did asteroids evolve? How did the surface of the moon evolve? And then translating those characteristics into spacecraft design. So how should we design a spacecraft to sample on an asteroid? How should we remove dust from a spacesuit? And then I also have like a section of work that is related to orbital debris and understanding orbital debris around Earth. So very much not a planetary science topic, but a topic that is related to dust and plasma, which are kind of my two areas of expertise. So the talk today, I have three sections. First, we're going to talk about electrostatic lofting and the subsequent motion of dust on the asteroid Bennu, assuming an undisturbed environment, so just the natural environment of the asteroid Bennu. Then we're going to consider lofting and dust motion once we have a spacecraft that is close to the surface of the asteroid Bennu. And then finally, I'll show some experimental work that shows that not only do individual particles get electrostatically lofted, but we could also have electrostatic lofting of clumps of particles. So, you know, a clump is where we have an aggregate of a bunch of different particles that are kind of sticking together and moving as one. Okay, so let's talk about an introduction to electrostatic dust lofting and what is it. So electrostatic lofting is this idea that dust or regolith could detach from the surface of an airless body due to interactions between the dust particle and the local plasma environment. Because the moon and asteroids don't really have an atmosphere, the surface of these bodies interacts directly with the solar wind plasma, and that causes the surface to charge up and also develop sort of a plasma sheath above the surface. And so the dust particles on the surface are charged and they interact with that plasma sheath, and that causes these electrostatic forces on a particle. So there are two phenomena. There's electrostatic lofting, and that's the detachment of the particle from the surface. And then there's electrostatic levitation. And levitation is this idea that a particle could hover above the surface because the electrostatic force is canceling out gravity. So they're two separate phenomena. They're related. They're both caused by electrostatic forces, but they're really two separate phenomena. So what evidence do we have that electrostatic lofting or levitation may actually occur? Well, the first piece of evidence came from the surveyor era. So this is, before Apollo. And there was this glow above the lunar horizon, and it was called the lunar horizon glow. And it was thought to be caused by light forward scattering off of dust particles that were hovering above the surface. So that was the first piece of evidence that maybe some non-gravitational forces are important here. Then during Apollo, an instrument was placed on the surface, and it wasn't intended to measure dust of lunar origin, but that's what the results have been interpreted as. So this is a histogram showing basically dust impacts on an instrument on the surface of the moon. And it's showing these, peaks in dust impacts at sunrise here, and at sunset. And so those instrument results have been interpreted as evidence that dust is moving around on the moon. But neither of these observations is really conclusive. There's still some uncertainty about whether or not dust lofting or levitation occurs naturally. But if you think that dust lofting or levitation does occur on the moon, then it's natural to extend that hypothesis to asteroids, because asteroids have a much weaker gravity than the moon, but they still have no atmosphere, no significant magnetic field in most cases. So if you think that dust is moving around on the moon, then it's probably also moving on asteroids. Now, the first evidence that something like that might be happening on asteroids came from the NEAR mission, which visited the asteroid Eros. And on that mission, they saw these dust ponds. So these, in the bottom of craters, a collection of small particles in the bottom of craters. It looks like a flat, smooth surface. And they call this a dust pond. And it was thought, well, maybe electrostatic lofting is causing particles to be deposited into these ponds. But nonetheless, we don't really have any conclusive evidence that these phenomena are occurring. So there's a lot of modeling and experimental work that's going on to try to understand these phenomena and then make better predictions about whether or not they occur in situ, and design dedicated instruments that could actually make some conclusive observations about whether or not these phenomena occur. All right, so now we're going to talk a little bit about the physics of electrostatic dust lofting and dust levitation. This is our surface of our airless body, and that surface is interacting with the solar wind plasma, which would tend to charge the surface negatively. And it's also interacting with the solar UV radiation. So the solar UV radiation causes photoemission, so it causes the regolith to lose electrons, and that tends to charge the surface positively. On the day side of one of these bodies, the photoemission wins, and you get a net positive charge on the day side of the body. Now, if we zoom in and we look at individual regolith particles, it gets a little bit more complicated. So in 2016, we really had a kind of a revelation in our understanding of how charging of individual particles works. And this is the general idea. So dust particles are insulators. That means they can have patches of positive and negative charge on the same dust grain. So if you have, say, photoemission and it illuminates a surface of one particle and that surface loses electrons, those electrons might get deposited on neighboring particles. So this surface is going to be positively charged because it's lost an electron. This surface is going to be negatively charged because it's collecting an electron. And that way you can have, charge building up between neighboring particles. So you could have all these red surfaces being charged negatively, all the blue surfaces being charged positively. Now, if because the particles are very close together, you can get really strong repulsive forces, right? So these red surfaces are going to repel from one another, but the particles are very close together. So that could make a really large repulsive force. And if that repulsive force is large enough to overcome gravity and cohesion that are holding the particles together, then that dust particle could be detached from the surface, right? It could fly away from its neighboring particles. And that's what we call electrostatic lofting, the detachment of the particle from the surface. Okay, so now zooming back out, if we just consider this positively charged, net positively charged surface in the solar wind plasma, it's going to attract electrons, right? It's a net positive charge. It's in a plasma. It's going to attract electrons. So that region of increased electron density is called the plasma sheath. And because there's some charge differential with altitude in the plasma sheath, it has an upward pointing electric field. Okay, so here's our dust particle on the surface, and the repulsive force between this dust particle and its neighbors is large enough to overcome gravity and cohesion. So now the dust particle is lofted. It detaches from the surface. Now, if it's lofted with just the right initial charge and initial velocity, that electrostatic force on the particle, so now the electrostatic force is Q, the charge on the particle, times the electric field. So there's this electrostatic force that is pushing the particle away from the surface or potentially towards the surface if the particle is negatively charged. So that electrostatic force could counteract gravity, and the particle could hover above the surface before it re-impacts in a region where the electric field is weaker. So that is the phenomenon of electrostatic levitation. So two separate phenomena: lofting, which is the detachment of the particle, and then levitation, which is this hovering of the particle. Now there's some other complicating factors. So if we stick a spacecraft on or near the surface, the spacecraft is going to change the plasma environment. The spacecraft is charged. The spacecraft also casts a shadow on the surface, and that changes the charging of the surface because it can't photoemit. So it's going to change the plasma environment, which complicates things. And then also, if you have like a rover driving across the surface, it's going to cause the regolith to charge up. So the charge on the regolith might not be exactly what we predict. So there are some additional complicating factors. All right, so now that we've talked about the physics of what's going on, we're going to get into the three sort of technical areas of the talk. And the first, we're going to just try to understand whether electrostatic lofting occurs on the asteroid Bennu and what happens to particles after they're lofted. Okay, so as I mentioned in the previous slide, in about 2016, there was a real change in our understanding of how particles charged. So again, we think that electrons are being emitted from one surface and then being accumulated on neighboring particles, and these neighboring particles can repel each other. And that repulsion is what we think causes electrostatic lofting. So in 2016, there were two theories that, two papers that discussed the same concept. One was a computational study, and one was an experimental study that then developed an empirical model of what the charge on a particle should be, or what the electrostatic force in the particle should be. So in this work, we implemented both of those charging models, both the computational and the empirical model, and we used that to predict the size of particles that could be lofted from Bennu. And Bennu is the asteroid that was visited by the OSIRIS-REx spacecraft. Okay, so this is the results from our first charging model. All right, so this charging model is the computational charging model. It basically assumes that two neighboring particles behave like two walls of a capacitor. So it uses that approximation to calculate the amount of charge on the neighboring walls of the capacitor and also the electric field between the neighboring walls of the capacitor. All right, so what we're doing, and in order to calculate the charge on one of those walls of the capacitor, you basically numerically integrate this charge density equation until you reach some steady state. All right, so what we're doing here is we want to see what size particle could be electrostatically lofted. What particle has a large enough charge that it can overcome the gravity and cohesion holding the particle onto the surface. Cohesion is really important on these airless bodies, especially asteroids, because gravity is weak and we have no atmosphere So particles, there are strong van der Waals forces, or we think there might be strong van der Waals forces between particles on the surface. So what we do here is we solve for the electric field that you would have to have between two particles in order to overcome that gravity and cohesion as a function of particle size, so particle radius. And then the black line and the blue line are indicating that electric field that you need for two different levels of cohesion. One is a weak cohesion, and then one is a strong cohesion. And we think that cohesion in Bennu's regolith is actually pretty weak. So we're going to be focusing on this black line here. The red line is the electric field that we believe to be present between two neighboring particles. So whenever this red line is greater than the black line, then those are particles that could be electrostatically lofted. So we think that all particles smaller than about 1 or 200 microns could be lofted from the asteroid Bennu using this charging model. Next, we did the same thing, but using the empirical charging model. So this empirical model has a much simpler formulation, a much simpler equation for what the charge on the particle would be, but it depends on this empirical constant eta. And eta can range from 4 to 10, but we don't know what it's dependent on. Another interesting feature of this model is that it predicts that the electrostatic force is independent of particle size, which is a little bit concerning to me. So I personally prefer the computational model to this model because I think that it is more based in the physics of the problem. Nonetheless, if we look at this plot, we see that this plot predicts that particles between, smaller than about 50 microns could be electrostatically lofted from the asteroid Bennu. So we have some agreement between these two charging models, even though they come from very different places. And that suggests that particles, 50 to 100 microns in size or smaller could be electrostatically lofted from the asteroid. Okay, so the next question is, after those particles are electrostatically lofted, what happens to them? Do they levitate? Do they escape from the asteroid? Do they re-impact? After the particles are lofted, we numerically propagate their trajectories. We're changing both the position, the velocity, and the charge of the particle as a function of time and location. And we consider an electrostatic force, a 1 over r squared gravity, so a simplified gravity, spherical gravity model, and then solar radiation pressure. We consider both positive and negative initial particle charges because we don't know the polarity of the particle charge when it detaches from the surface. So the computational model does not specify if the particle should be positive or negatively charged. Experimental work suggests that most particles are negatively charged when they're lofted. So we explore both options. And then we turn off the electrostatic force once the solar incidence angle gets larger than 80 degrees. So once you get towards dusk or dawn, then we turn off the electrostatic force because the plasma model that we're using is a semi-analytic model, and it's not very accurate once you get in these dawn, dusk, or nighttime regions. All right, so what are the initial conditions of the particles when they're lofted? This is looking at the computational charge model. And again, we're most interested in the weak cohesion case. That's the red dotted lines here. So particles, we believe, are lofted with an initial charge around 10 to the minus 16, 10 to the minus 15 coulombs. We think that they have initial speed that is much less than a meter per second, so probably less than half a meter per second. Here are some trajectories for 1 micron particles. Again, each individual particle is numerically integrated by itself. There are no interactions between the particles. I just plot them all on the same plot so we can see them at the same time. All right, so we're looking down on the North Pole of this asteroid. This point here is high noon. The sun is over to the right. The asteroid is rotating counterclockwise. The solar radiation pressure is flowing from right to left across the screen. So what I'm doing here is I'm lofting 3 particles, one at high noon, one at 30 degrees, and one at 60 degrees. And I'm using the computational charging model to predict their charge and giving them a negative initial charge. So when we look at these trajectories, we see that all 3 particles escape from the asteroid. We also see that if we just plot the trajectories in terms of altitude as a function of time, we get this altitude oscillation, and that is electrostatic levitation that we had talked about in the beginning of the talk. So this model predicts that for these 1 micron particles, they could be lofted at a variety of different times during the day, and they may electrostatically levitate before escaping from the asteroid. We can also look at how speed and charge vary with that particle. We see that particles are lofted again with these very slow speeds, and then they're accelerated due to that solar radiation pressure pushing the particle away from the asteroid. We also see that the particles are lofted initially with a negative charge, but very relatively quickly become positively charged. And then this constant charge out here, this occurs when we turn off the electrostatic forces when the particle gets close to that dusk terminator. So our model it's not very accurate there. So we just turn off electrostatic forces and assume that the charge is constant after that point. We can look at the same thing, but now assuming that the particles are initially lofted with a positive charge. Here we do not see any levitation. We see that this particle just has kind of a ballistic trajectory across the surface and re-impacts, but the particle that's lofted at 30 degrees gets very, very close to the surface, but still escapes. And the particle lofted at 60 degrees also escapes. So we don't really see any levitation. We still see that particles escape, but we see that, maybe a particle could experience multiple hops prior to escape. So you could have a particle that is lofted at high noon, re-impacts, and then is lofted again, say at 30 degrees, and then escapes from the asteroid. Looking at the empirical charging model with a negative initial polarity, we get very similar behavior to that previous case. Now, these particles are lofted with an initial velocity of 0.5 meters per second. Again, we see no levitation, but we do see this potential for particles to hop across the surface prior to escape. We can also look at the lofting of larger particles. Here we're looking at 10 micron particles and 100 micron particles. For the 10 micron particles, we see, again, hopping prior to escape. For the 100 micron particles, for each of the cases considered, the particles re-impacted, so they did not escape from the body. You could potentially have one of these 100 micron particles escape if it was lofted very close to the terminator, but our plasma model is not great at the terminator or that sunset condition, so we did not explore that any further. So the conclusions for this section, we have implemented the state-of-the-art regolith charging models, and they suggest that particles smaller than about 50 to 100 microns could be lofted from the asteroid Bennu. These lofted particles may levitate prior to escaping or escape directly or re-impact. We also see that solar radiation pressure is a significant force in prompting the escape of the particles. It is really active in accelerating the particles away from the asteroid. And this combination of electrostatic lofting plus solar radiation pressure could be a significant particle loss mechanism for the asteroid Bennu. And this work has been published in just this year in the Journal of Planetary Science. Okay, so now we're going to look at electrostatic dust motion, so the same topic, but now we're going to see what happens when we include a spacecraft near the asteroid. We're using a very simplified spacecraft model. Our spacecraft is just a rectangle. It is at some height above the surface. It has some size, and we consider 2 different directions of the solar wind, essentially 2 different times a day. First, we'll consider theta equals 0. That is high noon. So if you had your spacecraft near the surface at high noon, and then we'll consider the case where the solar incidence angle theta is 76 degrees. So this case is the condition, the illumination condition that was present when OSIRIS-REx actually executed its sampling maneuver. Now, again, the presence of the spacecraft is going to change the plasma environment because the spacecraft itself is charged and it will cast a shadow on the surface. That shadow is going to prevent the surface from photoemitting. Our goal is to understand how does the dust behave in this more complicated, modified plasma environment. The plasma simulations were done by my collaborator, Mike Zimmerman at APL, and it was modeled using a 2D in-house tree code to model that plasma environment. It's a fully computational environment. The spacecraft is electrically floating. Spacecraft in these models does not photoemit, so that's something that we're working on changing right now. And then the spacecraft is modeled at each height independently. So we do not actually model the descent of the spacecraft to the surface. We just place the spacecraft at an altitude above the surface and then model the plasma around that spacecraft. So we're not including any sort of transient effects. And we're assuming that the plasma environment is constant throughout the trajectory of the dust particle. Here are some of these plasma results. Our spacecraft is this rectangular box here. We're looking at, altitude, and then on the x-axis is just our lateral extent. We're looking at a 5 meter long spacecraft, 3 meters above the surface of the asteroid. The top row is for the solar incidence angle of 76 degrees, and the bottom row is for the solar incidence angle of 0. That's high noon. We plot the electron density, the ion density, and the photoelectron density. Remember the photoelectrons are emitted just from the surface. They're not being emitted from the spacecraft. So you can most clearly see the effect of the spacecraft in the ion density because the ions are very heavy. So they are not able to fill in the wake region behind the spacecraft. So this is the wake behind the spacecraft. There's not many ions there. And we can again see the wake, which corresponds to the shadow in the high noon case. When we look at the photoelectrons, we see photoelectrons being emitted from the surface. We see that there's fewer photoelectrons beneath the spacecraft here because the spacecraft is negatively charged, so they're kind of repelled from the spacecraft. The negative electrons are repelled from the negative spacecraft, so we don't see many in this region right below the spacecraft. And then in the bottom plot, we don't see photoelectrons beneath the spacecraft because the surface there is shadowed, so it's not emitting photoelectrons there. Now we took our particles and we gave them the initial conditions that they would have from our electrostatic lofting simulations, like I showed in the previous work. And then we numerically integrated the trajectories of the particles in this new plasma environment. Here are some particle trajectories. The dashed lines here just show you where the shadow is. This left case is the solar incidence angle of 76 degrees. And the right case is the solar incidence angle of 0 degrees. So the shadow is directly beneath the spacecraft here. And note that we only loft the particles on surfaces that are illuminated. We cannot loft particles in surfaces that are in shadow. So all of this region down here is sunlit, and we can loft particles from those locations. And then for the high noon case, we loft particles, outside of the shadow of the spacecraft. And we see in all of these cases that the particles stay pretty close to the surface, and they are repelled from the wake of the spacecraft. All right, now we'll look at the effect of the spacecraft more directly. In order to do this, what we did was we compared the case when the spacecraft is 50 meters above the surface to the case when the spacecraft is 3 meters above the surface for the solar incidence angle of 76 degrees. When the spacecraft is 50 meters above the surface, it's so far away from the surface that the surface basically doesn't know that it's there. Any charge from the spacecraft is shielded out by the plasma between the spacecraft and the surface. In this case, we see that, a particle is lofted from the surface and then has this short hop before re-impacting. When we bring the spacecraft much closer to the surface, now the spacecraft is interacting, the spacecraft's charge is interacting with the surface. And now we see that the particles are repelled from the spacecraft and also from the wake behind the spacecraft. And that is causing the particles to move to the left in this plot. And we see, so that's causing the particles to move to the left in this plot. We see that giving the particle an initial positive charge actually attracts the particle to the spacecraft briefly before the particle's charge goes negative, right? So the particle is initially positive, and then quickly becomes negative. So that initial positive charge that at first attracts the particle to the spacecraft kind of gives it an additional kick that causes it to travel much further before re-impacting. We can also look at the effect of the initial position of the particle on the trajectory of the particle. This is on the left, the solar incidence angle here is 0 degrees, and on the right, the solar incidence angle is 76 degrees. So first we'll start with looking at the case on the right. For this case, we see that all of these initial particle locations, I've just, to plot them, I have translated everything so they all start at 0. So the x-axis is just the translation of the particle. So you can see the impact of initial particle location on the trajectory. So when we look at this case where solar incidence angle is 76 degrees, we see everything is being pushed left. Everything is starting at one location and then translating to the left. And that's because the wake behind the spacecraft is to the right. So all of these particles, which we initially loft with a negative charge, are being repelled from the spacecraft and repelled from the wake behind the spacecraft. If we look at the case of high noon, so the shadow is directly below the spacecraft, we note that we can only loft the particles in illuminated locations. So what we're really doing is we're seeing, as we get farther and farther from the edge of the spacecraft, how do the trajectories of the particles change? If we look at the particle launched directly below the edge of the spacecraft, it has this very long trajectory. So it is getting an additional, sort of an additional kick due to the fact that there are these fringing and strong fields at the corner of the spacecraft. And then as we move away from the spacecraft corner, we get shorter, we get less X translation. And we also have symmetry whether we loft particles to the left or the right of the spacecraft because the sun is directly overhead. So we have modeled the plasma environment near a floating spacecraft, and we see that lofted particles very quickly charge negatively. We also see that the electrostatic forces tend to accelerate the particles away from the spacecraft, although this could change when we start including a photo-emitting spacecraft in the simulation. And that's the part of the project that we're working on currently. So we hope to get this work out in the next year once we include photo emission on our spacecraft. All right, now the final topic of the discussion today is going to be some experimental work on lofting of clumps. This work was done by my grad student, Charles Pett, and most of the slides are actually by him as well. There have been many experimental demonstrations of electrostatic lofting, especially by Xu Wang at the University of Colorado. And all of those experiments have really considered lofting of individual particles. But we know just from our day-to-day experience that cohesive powders often move as clumps. If you take baking flour, and you're making bread, you know that powder is very clumpy. And so it's likely that if you have a cohesive powder like regolith on an asteroid or the moon, that you'll also get clumps in that regolith as well. So the goal of this work is to show that that clumps can be electrostatically lofted, and to try to understand the size of those clumps as well. Here is our experimental setup. We have a vacuum chamber. We have a plate in the vacuum chamber, and we have a series of piles of silica zirconia grains. At the top of the vacuum chamber, we have an emissive filament. So this is emitting electrons, heats up, emits electrons, and those electrons charge the dust on our graphite plate. We also have a plate above our grains that attracts the grains. So this upper plate, this electrically biased upper plate, creates an electric field pointing up from the particles. So it attracts the dust particles. And that electrically biased plate actually also serves to concentrate the charge from the emissive filaments on the particles that we're trying to move. And that's what this simulation on the right is showing. It's just showing some trajectories of electrons moving around this electrically biased plate and showing that they actually get focused on the dust particles on the graphite plate. All right, so on the left, hopefully you can see the video. So there's a video showing motion of clumps. I will play it again here once it finishes. All right, yep, it's playing again. So you can see right here, you have a clump of like 4 particles. It looks like a chain. It detaches from the surface and then re-impacts. All right, and here are some close-up videos that show some 2-particle clumps, and then this looks like a 4-particle clump. And they have these kind of parabolic trajectories prior to re-impact. These particles are 200 to 300 micron zirconia silica microspheres. They're very spherical particles, and they're pretty large, 200 to 300 microns in Earth's gravitational environment. Now, we note that we're not trying to mimic the plasma environment or the charging environment on the moon or an asteroid. We're just trying to show that clumps can move in addition to individual particles. Now, these particles are spherical. We know that regolith particles are not spherical, and they're also a range of different sizes. We're using spherical particles here because we can compare these clump sizes and motion to prior models that we have that would predict the size of clumps that should move around. However, we also see that when we use just basic baking flour, that we also see clump motion with baking flour in this experiment as well. So some of our future experimental work is going to analyze and compare the baking flour, which is a polydispersed aspherical mixture, to this work with the silica microspheres. We can look at the prevalence of clumps, how often are clumps lofted versus individual grains. And that's what we're showing here in the left plot. So we compare the number of grains lofted to the number of clumps lofted in our observation window. And we see that the clumps are a fairly significant portion of the number of objects that are lofted. That means that if we think that lofting occurs on an asteroid or the moon that has a cohesive regolith, it's likely that we would have lofting of both individual grains as well as clumps. We can also solve for the tensile strength of the regolith by looking at the trajectories of the particles. With our camera, we observe the particles across their trajectory. We can identify the position in each frame. From the position in each frame, we can calculate the velocity and the acceleration of the particles. And by looking at those, we can calculate the the acceleration of the particle at the instant when it detached from the surface. And that acceleration at the instant that it detached from the surface, that basically gives us the cohesive force on the particle at that instant of detachment. Because we know when the particle detaches from the surface, that cohesive force is instantaneously broken. So whatever that initial impulsive upward force on the particle is when it detaches from the surface, that is equal to the cohesive force that was acting on the particle but is now missing. So we can solve for that cohesive force, then we can divide it by a surface area, and that gives us really a tensile strength, not a cohesive force here, for particles and for the regolith simulant that we're using. So the tensile strengths that we're getting are, between about 10 and 100 pascals, which is pretty reasonable considering, behaviors of powders in vacuum. In conclusion, we have experimentally demonstrated that electrostatic lofting of clumps is possible, and that clumps could be a non-negligible component of the lofted object population. Thus, we predict that if electrostatic lofting occurs in situ, we will likely see clumps lofted in addition to grains. We can also solve for the cohesion on the regolith if we can image the trajectory of the lofted clumps. And our next step is to start comparing the clump sizes to our analytical predictions of what size clumps should exist. We're currently working on a publication with this work, and hopefully it will be submitted in the next month or two. So now I'll just give an overall summary for the full talk. So electrostatic lofting are two different but related phenomena. Lofting is the detachment of the particle from the surface, and then levitation is this oscillation of the particle above the surface. We have implemented state-of-the-art charging models to predict the size of particles that could be lofted from Bennu, and the trajectories of the particles after they've been lofted. And we show that these small particles could escape from the asteroid. We've also modeled the plasma environment near a spacecraft near the asteroid. And in this work, we see that dust is repelled from the spacecraft and its wake, although our ongoing work is going to include spacecraft photo emission, and that could change the results somewhat. And then finally, we have experimentally demonstrated that clumps of particles can be electrostatically lofted in cohesive powders. So with that, I would be happy to take any questions.
Yeah, thank you so very much, Christine. Yeah, a very nice talk, and has many things in it. So let me first ask the audience, do you have questions? You could raise your hands or just ask. Yes, Lin Ji-hong, you have your haircut, new haircut. Yeah, Ji-hong.
Okay, so good morning, Professor. So I have one question is, so just like you say, so when the solar radiation, they penetrate the surface of the granule of the asteroid, it can be caused this charge separation. So my question is, because we know that many asteroids will be entered to the orbit that very, very close to the sun. So in this time, the inferior asteroid, their surface will be burning by the extremely strong radiation. So in this kind of environment inside, is that possible that the granulations in the asteroid surface and their repulsion speed by the charge, it can be rising to the escape speed of this asteroid? So that's just the first question. Thank you.
Yeah, so I think that when particles are lofted from the surface, I think they will be lofted at a speed lower than the escape speed. But I think that they may escape from the asteroid due to acceleration from the solar radiation pressure.
Okay, so my second question is because we know in some comets that 67P, this kind of comet, so their surface is very loose and very soft. So this is made by some very, very thin granulation, and it has a very high porosity. So my question is, because in theory, if one of the materials is made by many very tiny granulation, so this granulation will be has a very strong friction force with the other granulation particle. So my question is, in this kind of surface, so even there's a charge, even there's a particle that can receive enough strong charge separate force, but because the friction force will be locked, there's a particle on the surface. So what the particle can success to escape from this kind of very high porosity material, or possibly just like something that electrosensitive material that their size will be changed. So when it has enough strong electroseparate force, this material, their size will be enlarged, and then when that rotate into the shadow size, and when the electron support forces disappear, and their size will be recovered.
So I think that this depends on the direction of the electrostatic force. If your direction of the electrostatic force is, say, pressing on the particle and kind of pushing it towards its neighbor, or pushing it so it gets locked with its neighbor and it has this high friction force, then yes, it would be difficult to electrostatically loft that particle because it's kind of getting locked by its neighbor. It really depends on the direction of the electrostatic force. We haven't done any modeling, any computational modeling of like a polydisperse mixture of aspherical grains. And those simulations would probably be pretty difficult to do, to model the charge transfer between different patches on the surface of grains of different sizes with different shapes. But that's in actuality what would be happening on an asteroid or a comet, where you have these additional friction forces.
Okay. Yes, Christine. So Chi-Hong is the student, the high school student mentioned to you. I hope that he will continue his interest, and at the end he could go to American to study.
That would be great. Yeah.
Right. There's another question by Ian Lai. His question basically is what is the efficiency of the electrostatic lofting of the dust?
I'm not sure. There has been some work that has tried to predict how effective electrostatic lofting would be as a loss mechanism on asteroids. So perhaps this mechanism could explain why we don't see many small particles on like Itokawa, but we do see many small particles on Eros. So Eros is a much bigger asteroid than Itokawa. So there has been some work that has looked at efficiency in terms of could electrostatic lofting be removing all of the small particles on Itokawa, but it's not efficient enough to remove all the small particles on Eros. I haven't done any work looking at efficiency, so there's not a simple answer to that question.
Good. Dr. Zhongyi Lin has a question.
Yes.
Zhongyi, can you tell us your question?
Very good, very nice talk. So, I have a question. Do we really see this micron-sized particle eject from the venue, from the spacecraft?
Do we see micron-sized particles?
Yes, you say, yeah.
No, definitely OSIRIS-REx, the resolution on the surface, I think, was in the millimeter centimeter range when the spacecraft was above the surface. During sampling, the spacecraft kicked up a bunch of dust off the surface, kicked up a bunch of particles, and they do have some idea of like the size distribution of those particles. I still don't think that they were able to see down to individual micron-sized particles. When the spacecraft returns the sample to Earth, then we'll be able to get a complete size distribution. But during the reentry process, there's going to be lots of high gravitational forces and shaking. So you could have some particles that break up either during sampling or during reentry. So I think our main evidence that there are not small particles on Bennu comes from just observations of the surface. It doesn't look very smooth at all, and also looking at the thermal inertia, which is another indication of the presence of small particles.
Yeah. I think that, Christine, I think you know that there's a recent paper in Nature Astronomy by Song Xu from Colorado about the effect of solar radiation pressure, that it could blow the small dust particle away from Bennu. Yeah, I think it's quite similar, you know. I mean, that he has to launch those particles first and to overcome the cohesive force. I do have one or two questions to you. First thing is that in your calculation, you assume that once you have the solar zenith angle larger than 80 degrees, you switch off the electric field.
Yes, so that is because our model is not good in that region. Like we use a for that first section of work, we used a semi-analytical plasma model, and it's just not accurate once you get past about 80 degrees. So we just turn off the electrostatic force there to avoid, making inaccurate predictions.
Yeah, and some standard model on the charging, you should start charging of the cometary nucleus on the night side. I think it was proposed by Asoka Mendes in the 80s.
Okay.
Is that it will be charged to, let's say, 100-volt negative or even keV negative, right? I mean, that kind of thing has been seen on the lunar surface too, on the night side.
Yeah. Yes. Yeah, I know that there have been large potentials predicted on the night side. It's kind of difficult when we applied the same sort of analysis where we looked at the feasibility of lofting due to the various charging forces. We looked at that for the night side as well, just considering secondary electron emission as the charging mechanism. And we were not able to predict that there would be enough charge on the particles for them to be electrostatically lofted at night on Bennu.
Well, I mean, that because the electrons, they even though the throwing proton would have been shielded, but they're not the electrons in the solar plasma. So that's why they're negative potential. The other things that I'm happy to see that you're going to take into account the photo emission of the spacecraft. Yeah, because the by shift would be on that order, a few meters. So once you get close to the surface, and the whole thing could be connect together, it would be very interesting, though very complicated situation. Yeah.
So that's why we were using a fully computational model for that, because there's no way we could model that analytically. But those plasma results, simulation results, should be done very soon. So then we'll run it through the same analysis and see what sort of results we get.
And also, I start to understand why you call your lab planetary surfaces and spacecraft.
Yeah.
Right. Very good. Okay. It's getting late here, though. Even you're in high spirit, Christine, because it's morning there.
Right.
So anyone in the audience want to ask questions, last questions? If not, and I would end this session, very interesting session. I hope to. I think that every time Christine publishes a paper, we invite her back to give a talk about it. That's
very nice. Thank you for the invitation. And,
thank you.
Yes, thank you for staying up late as well.
Yeah, have a great day. Yeah.
Bye.
Bye-bye.